Share screen. Okay, so welcome to the 10th class of this electromagnetic theory. And if you remember, in the last two classes, we had been discussing about transmission lines, and then we also discussed how Smith charts can be used to find out, the distributed parameters of the transmitted lines, or can be used for impedance matching in using graphical methods. Okay, so that was about the last class. In today's class, what we'll try to do is we'll try to see uh, what are waveguides. Okay, and we'll start with first discussing how waveguides are different from transmission lines. And when we talk about waveguides, what are the different conditions which determine the kind of signals or kind of waves that can be transmitted through the waveguide. So we'll try to discuss all that. Okay, so that's about today's class. Now, first let us see how transmission lines are different from waveguides. Right. So here, as you can see, in a transmission line, what we had already discussed before, we have something like this, right? So where there is a load impedance somewhere, it can be purely resistive or it can have some inductive or capacitive load here. So this is some load, and then you have some source at the other end, and then they are connected by some transmission lines. And what we saw is that these transmission lines affect the kind of signals that one sees at the load end, right? So the voltage that one sees here is different from what we see here, right? And when we talk about voltages, voltage is nothing but, like, if you look at the definitions, we know that voltage is nothing but the line integral of electric field, right? So in a way, that means that the electric field, there is a change in the electric field, right? So if you consider this to be a source, then if it is the positive terminal and this is the negative terminal, we know that there'll be a voltage difference ends, and these two are two different conductors. And here you can see that if there's a this is a positive terminal, this is a negative terminal, we know that there can be an electric field in this direction, right? While the signal gets propagated along the transmission line. Now, as the signal gets propagated, we know that there's a current flowing through it, right? And when there are current flowing through wires, we know that there's a magnetic field that can be associated with it. And if you consider this to be a current carrying wire in this direction, suppose this is Z, then we know that the magnetic fields will be in the Y direction. Right? So that means in this kind of transmission lines, we have, we in general, like transmission lines are, they comprise of, no, at least two conductors, as you can see here, right? Even when we talk about coaxial cables, we know that there's a positive uh, terminal, there's a negative terminal, and there can be dielectrics in between them, but they're mostly, they include two conductors, right? And as you can see here, the electric field or the magnetic field that can be associated with the signal are perpendicular to the direction of propagation of the signal, right? So that means transmission lines support TEM mode. What do we mean by TEM? So TEM is transverse electric and magnetic fields. That means the electric and the magnetic field components are perpendicular to the direction of propagation of the signal. Okay, and they're mutually perpendicular as well. So that means transmission lines support TEM modes, and as you can see, there are two conductors that are involved, and generally transmission lines work quite well for at least till few gigahertz range, in the gigahertz range. Okay, at least till that. But now, when let us come to waveguides. Now here you have two conductors. Imagine if you now have only one conductor. Okay, so just conducting, closed boundary maybe. Okay. So then what happens? So now the question is, if you have just a conductor, what are the kind of signals that can be transmitted through them? Okay. And here we'll come to it from from the derivations. Why in this kind of cases where there's only just one conductor, their TEM modes are not supported. So what we get is transverse electric or transverse magnetic modes. It supports various higher order modes, but TEM mode is not supported. Okay. And we'll see that this based on the dimensions and the structures of the waveguide, one can use it till much higher frequencies, at least in the terahertz range. Okay. So this is the major difference between transmission lines and waveguides. Now let us understand from starting from our known knowledge of Maxwell's equations that how what determines the kind of signal that can pass through a waveguide and what might not. Right? So what are waveguides? Basically, when we talk about waveguides, it's like a hollow pipe. Okay. So you can consider that in we know that in free space we have electric field and magnetic field, which they are mutually perpendicular to each other, and there can be waves which are electromagnetic waves, and then the direction of propagation of the waves is perpendicular to the electric and the magnetic field. That is what happens in free space, right? So in free space we have TEM modes. Now consider the case where you have a hollow pipe with the surface being a conductor. Okay, so some hollow pipe where the surface is actually conductor. Okay, and you want to see what kind of signals can flow through this pipe. Okay, so that's what we are trying to find. Now here, because as you can understand, because there is this conductor, that means there is a new boundary condition that is now being established, right? If it was free space, that means it can be any electric or magnetic field value somewhere here. But now because you have a conductor which is enclosing this region, that means here we know that in a conductor the electric field is zero, right? We know that here the magnetic field is supposed to be zero. So that sets the boundary conditions for our problem. So that means whatever signal we have here should satisfy the boundary condition of the tangential component of E going to zero in the inner walls of this conductor, and the normal components of the magnetic field should also be zero. Now, how do we get to these boundary conditions? We get it from the Maxwell's equations, right? So from this relation, we can see that we can get the tangential this condition for the tangential components, and we know the divergence of B is zero. So from here we can say that B normal should be equal to zero, right? So now that we know that these are the boundary conditions that are to be satisfied in the inner wall, what should be the wave like inside? That's the question, right? So in general, if you talk about monochromatic waves that can propagate, they would have a generic form of something like this. So you have some complex, amplitude here for E and B, and then you have something like e to the power I kz minus omega t, right? That is the generic form of the electric or magnetic field. In general, we are just considering it to be some propagating wave. Okay. Now, these are the Maxwell's relations that needs to be satisfied. And we know that these are the boundary conditions. These are the values that are to be satisfied at the wall. Now, given this condition, what do we do now? So what we do is we now write the electric and the magnetic fields in terms of the components. Okay. So EX, EY, EZ and BX, BY, BZ. And now if you just look at this second and the fourth Maxwell's relations, we can try to expand these relations in terms of the components. Right? And if we do that, this is what we will get. Okay. So from here, now if you just come, look closely in equation 2, 3, 5, and 6, you see that you can write EX, EY, BX, and BY in terms of this derivatives. And these derivatives are derivatives of EZ and BZ, right? Now, what is EZ and BZ? So if you look at the waveform of the electric and the magnetic field, you see that these waves are propagating in the Z direction. That means now you have components in the propagating direction. Okay. So when you have TEM modes, that is transverse electromagnetic waves, in those cases, your electric and the magnetic fields do not have any component in the in the propagation direction. So their Ez and Bz are expected to be zero, will be zero. But here, what you can see is that from these four equations, you can write Ex, Ey, Bx, and By in terms of the derivatives of Ez and Bz. And that means now if your Ez and Bz are zero, all of this will turn out to be zero. That means there is no wave that exists. So because of this additional boundary conditions that are coming in, we are now seeing that in these cases, you do have components in the propagating direction. Okay. And this is also telling you that now if you know Ez and Bz, you can actually find all of this. Right? If you know Ez and Bz, you can do this derivatives to find Ex, Ey, Bx, and By. Right? Now, how do we understand or how do we find Ez and Bz? So if you now look at the other two Maxwell's relation, that is the first and the second Maxwell's relations, and if you use this relations, okay, if you put it here, what you would get is two such uncoupled differential equations, right? And you can see that this is one differential equation which just involves Ez. There's another differential equation that just involves Bz. And from here, you can now try to find how your Ez and Bz should look like, right? But one thing is clear from here already is that if you have such kind of a waveguide or some, boundary with a conducting surface, and there are these conditions, boundary conditions that need to be satisfied, then TEM modes do not exist. And there, so in a hollow waveguide, TEM modes do not exist. And what we can have is TE or TM modes, where one of the BZ or EZ components are zero, but both of them cannot be zero. If it is zero, then everything turns out to be zero. Okay. Okay, so now we want to see how we can use these relations to find Ez and Bz and therefore all the other components, right? So here, let us consider TE waves. What do you mean by TE waves? That means transverse electric waves. So because it's transverse electric, that means Ez is zero. Transverse electric means the electric field is transverse to the direction of propagation of wave. That means there should be no component of electric field in the propagating direction. So Ez is zero. So you only have Bz. Now we know that this is the condition, right? This is the relation that Bz satisfies. Now, how do we find Bz? So in general, if you have such kind of a rectangular waveguide with some given dimensions, as given here, A and B, so you can understand that when you have this BZ components, it will have some dependence on the X and Y components as well, X and Y variables, right? So what you can consider is you can consider B to be function of X and Y as as a product, right? So this is just like the separation of variables that we had done previously. So here, now if you consider B as a function of X and Y like this, you can put it in the differential equation that we just got from here. That is this differential equation. And if you do that, you would get something like this. Okay, so divide by it, and then you would get independent terms, right? So basically, you're doing separation of variables. So here you can see that so if you just look at this part, you know that if you try to find the general solution for this part, it would have a some form like this. Right? Similarly, y will have some form like this, with the given condition that if kx and ky are the components of the wave vector, then this is the relation that it should satisfy, right? Where k, so this k is in the direction of propagation of your, this is the component of your, this is kz basically. This is component of your wave vector in the direction of propagation of your wave. And these are the other two components, kx and ky, right? And this just comes from the definition of your wave vector. Okay. Now here, if you just look at this is a general solution for this kind of a differential equation, right? Now we have to put the boundary condition. Okay. Now what is the boundary condition? So we saw that the boundary conditions require Bx and hence dx dx to be 0 at x equal to 0 and x equal to a, right? Because if this is a conductor, that means your normal components of magnetic field should be 0, right? At the boundary, at the inner wall. So because now Bx is 0, okay, So if Bx is 0, that means you can see here Bx depends on del Bz del x, right? So now if you have defined Bz as x into y, that means if Bx is 0, del capital X del x should go to 0, right? So this is a relation which is telling you that you have to satisfy this condition. So now that you know the general form of x, you can do a derivative and you can try to put this condition at x equal to 0, this is 0, at x equal to a, this is 0. So if you do that, you get this values, the possible values of kx, which is given as m pi by a, right? And m goes from 0 to all the integral values. Now, similarly, you can do the same thing for y and you'll get all the possible values of y. And here you can see this depends on the dimensions of your waveguide, right? So now you can therefore put these values and you can conclude that your Bz should have a form like this, right? This is coming from here. Just by putting x and y here, you would get this kind of a form. So this is the general expression for the Bz of a TE mode, where TEMN corresponds to this, you know, the what is the mode? So you define the mode by M and N. Okay. So generally, the first index is conventionally associated with the larger dimension. Okay. So now here, if this is your Bz, so now you know Kx, you know Ky, and if you say that, okay, my wave is propagating along Z and the total amplitude should, so if it is in, if there is no dielectric here, so you know that the velocity of the wave should be C. So from here, you can try, if you know the frequency, you know that this is the relation that your wave number should hold. Now, this is telling you something interesting. It's telling you that now if your omega is less than this value, what is omega? The frequency. So if the frequency is less than this value, which depends on the dimensions of your uh, waveguide. So this was for some m and n and some combination of m and n given some values of a and b. If your frequency of your signal, if it is less than this value, then the wave number becomes imaginary. Now, what do you mean by wave number becoming imaginary? So you can understand that if the wave number becomes imaginary, that means here you will, if you put it here, you would get an exponentially decaying turn, right? So that means then the wave will not be a traveling wave, but an exponentially attenuated wave. So this tells us that there is a cutoff frequency below which waves do not propagate. So frequencies less than this cutoff frequency do not propagate, while frequencies higher than that propagate, right? So that puts a cutoff frequency. So that means the waveguides here is acting like a high pass filter, right? It's allowing only higher frequencies to pass. Okay. Now, what can be the lowest cutoff? So the lowest cutoff means now you have to look at what could be the possible lowest value of M and N, right? So if M and N both are zero, that means the entire term becomes zero, right? So that doesn't make any sense. But you can put one of them to be zero, right? And if you put, the so now which one should be zero? So if you have to find the lowest cutoff, how do you do that? So there you have to consider what is the smallest dimension. So if you make the what do I say? So here n corresponds to along y direction, m corresponds for the x direction, right? So now if a is greater than b, that means m pi by a for a particular. So if you just take consider m equal to 1 and n equal to 1, then pi by a will be smaller than pi by b, right? So that means the lowest cutoff will be for the case where you make the smaller dimension, the mode value corresponding to the smaller dimension go to 0, while the other is just 1, the first non-zero value, right? So that means the lowest cutoff frequency will be TE10. So if you put TE10, this is what you get. So here A corresponds to the larger dimension of your waveguide. Okay. This is the expression for the cutoff frequency, lowest cutoff frequency. Okay. While this is the expression in general for any particular mode, this would be the cutoff frequency expression. Okay. Okay. Now, One second, guys. Okay. So now if we define a term, okay, omega mn corresponds to the cutoff frequency for that particular mode, okay, which is given by this relation that you see here. This is omega mn. Then you can write k as root over of omega by c whole square minus omega mn square, right? Something like this. And now that you know the wave number, you know how to write wave velocity, right? Velocity is nothing but omega by k. Okay, so if you do that, this is the expression for your wave velocity. Now, once you have this value, you can see, interestingly, this is much greater than c. So you might think, how is it possible, right? But this is possible because this is the phase velocity corresponding to a particular frequency. But this is not the frequency or not or you can say this is not the velocity with which the wave is traveling, or the energy is being propagated. The energy is propagated at the group velocity. And how do you find the group velocity? This is the relation, right? So now if you use this relation, you would see that this is still less than c, so everything is consistent, right? There's another way of looking at it. So this propagation of electromagnetic waves in a rectangular hollow waveguide, you can also look at it from this perspective that, if you have some boundary, okay, so some surface, and when you have some wave propagating, considering that, you're moving from a denser to a rarer media, and consider that there is total internal reflection that can happen, right? So there'll be multiple reflections as the wave hits at different the surfaces of your of the enclosing boundary. And now because, so suppose if there's a wave from here, it comes, it strikes, okay, it gets reflected, again it gets reflected here. So that means there'll be multiple reflections, and that can result in standing wave patterns. Okay, now what would be the wavelengths? So that will again be determined by the dimensions. So this is how the wavelengths will look like, and this is how you can see it depends on the dimensions of your wave guide, right? So from here again, you can write an expression for the propagation vector. Okay, it's the same value that we had initially we had seen here, right? So the same thing can also be considered in terms of total internal reflection, while where the waves are getting reflected from the different surfaces of the enclosing waveguide, right? And now if you know the wave vector or the propagation vector, you know what is the frequency, right? Omega is equal to c into k. So this is the same relation that we had initially derived. Now you know the expression in terms of the frequency. Okay. Now here you can find the component. Okay. This is the wave vector, uh, which is showing the direction of propagation of the uh, basically it can have all the three components, right? Now, if you want to see what is the component of the wave number in the direction of propagation of the wave, you can take a component, right? That component, like k prime cos theta, okay, will determine the net velocity with which the signal or the energy is being propagated, right? So there, if you find the cos theta component, okay, and then Bg is equal to c cos theta, so this is the same term as you can see here, right? So you are getting back the same expression for the group velocity, okay? So what do we understand from here? We understand that in a waveguide, because of this boundary conditions that need to be satisfied at the boundary of the enclosing surface, there are certain modes which can propagate, and there's a cutoff frequency below which things get attenuated, above which things get propagated, right? And that depends on what is the dimension, okay, and what is the mode we are talking about. So this is the cutoff for a given mode. This is how the omega looks like. So from here you can write an expression for the frequency, right? And this is how the expression will be. It's important to note. So if there's a question, or if you are asked what are the different factors in which the cutoff on which the cutoff frequency can depend, right? You can very well understand that it depends on the dimension of your waveguide. But there's one more factor. So here, what is c? C is basically the velocity with which the wave velocity, right? Now, when you talk about just a just a conductor with air inside, like free space. So there the velocity will be c. But consider now if you have a dielectric inside, so then the velocity will change, right? So basically this c will then be replaced by the net velocity for that medium, right? So in general, for free space, we know that C can be written as 1 by root over mu naught epsilon naught. For any other dielectric, you would have it as 1 by root over mu into epsilon, right? So that means the cutoff also depends on what is the medium that is there inside the dielectric, okay? So it depends on the dielectric properties or the material properties of the metal that is there inside. Okay. So it depends on dimensions and it also depends on its material properties. Okay. Now let us talk about TM modes. Okay. So for TM modes, it would be now Ez is not equal to 0, but Bz is 0. Why? Because it's transverse magnetic, right? So now Bz will go to 0. So just as we had done for the last case, now here we'll consider Ez to be function of x and y, okay? And we would get similar expressions. The boundary conditions though will change. Why? Because now we are looking at Ez, right? We want to see what is the boundary condition that Ez needs to satisfy, right? So here you can see that for electric fields, right, we know that the parallel components, the tangential components should go to 0 at the inner wall. That means here your Ez should go to 0. Initially, there what we were seeing is the normal components for magnetic fields, the normal components were going to 0. So we had to have Bx to be 0. That's why we did a derivative, right? Here we see that the boundary conditions require Ez to go to 0. So now this is your expression. So you can put x equal to 0 and x equal to a and see what are the possible values of kx. And similarly, you can do the same for ky to find the possible values of kx and ky, right? And this is what you get. So here, as you can see, what is the there's a difference, right? Initially, for the last case, you had cos terms here for TE modes, and there your m and n started from 0. Here, if you start m and n from 0, that means the entire Ez component will go to 0 because sine 0 is 0, right? So for TM modes, the the smallest mode or the first mode start from n and m being 1. Okay, they cannot be 0. Okay, and rest is the same. So now the expression for the cutoff frequency is the same. But if you are asked what is the lowest TM frequency, then you have to put M and N to be 1, right? While there you had put 1 to be like N to be 0 and M to be 1, right? So that's the only difference that you are seeing here. But other expressions remain the same. So that's how, in a waveguide based on the properties of the medium and the dimensions, you can have different kinds of modes, okay? And they can have different cutoff frequencies given by this relation, as you can see, okay? So now there was this kind of a question in the last year's assignment, which said that an airfield 5 by 2 centimeter waveguide has Ez given by this relation, okay? What mode is being propagated? Okay, so here you can ask that, given this condition, can you say, what mode would be propagated? Okay, so how do we answer this question? So here what we have to do is, this is the Ez component, and you can see it involves sine terms, right? Product of sine. And you know what is your A and what is your B, right? A is 5, B is 2. So now if you compare this expression with this expression that you have here, you can find what is M and what is N, right? So that is what you are being asked to find. So in this kind of questions, if you're asked, so your Ez component is given, you're asked what is the mode, right? So then compare with this form, because it has like product of sine, that means it's a TM mode, that is for sure. Now TM, what is the value of N and M? Compare this with this expression that you have here, and that will give you the value of M and N, right? So that's how these questions could be answered. Now, this is another question which says that uh, if in a rectangular waveguide A is equal to 2B, the cutoff frequency for TE02 mode is 12 Hz, we have to find the cutoff for TM11 mode. So how do we address this, right? So first thing is, we know the relation between A and B. We know the cutoff frequency for a particular mode in TE mode, like TE mode, right? we have to find the cutoff frequency for a different TM mode. So what we can do is we can use this relation, right? So here for the first case, we know how A and B are related to each other, so we can substitute one for the other, right? And we know what is M and N, and we know this omega value. So from there, we can try to find the value of B maybe. Once we find B, we can find A from there using that relation, and then try to use that to find the cutoff for the TM11 mode, right? So this is what I mean. So this is the normal uh, relation. So it's important that when you are talking about hertz, you have to use this relation. Okay. Remember to use, see here when we first talk, we are talking in terms of omega. But when your question is given in terms of hertz, you have to use the relation between omega and frequency, right? And this is the relation. So use this relation. So now here what you can do is you can replace A equal to 2B, okay? And you can put this value M equal to 0, N equal to 2. And from here try to find the value of B. Now, once you find the value of B, you can again put, B, so you can find A. And now you can again put in the same expression and try to find the cutoff for the other mode, right? So this would be the answer. So they're very straightforward questions, making use of the concepts and formula that we just derived. Okay. Now, the waveguide can be considered as high pass, low pass, band pass, or what kind of a filter? This is something we had already discussed, right? Because we just saw that there's a cutoff below which the wave number becomes imaginary and so the wave gets attenuated. Only above a particular cutoff, the propagation happens, right? So that means a waveguide is a high pass filter. Okay. Now, here, as you can see, there can be this kind of questions which says that, it's a air-filled metallic rectangular waveguide with the dimensions given. A and B is given. Which of the statement is true? So how do you answer this question? So now you know A and B. Okay, it's air-filled, you know that. Okay, so that means what you can do is you can try to find the lowest cutoff frequency for this case, right? So if you find the lowest cutoff frequency for this case, making use of this relation, right? So if you use this relation to find the lowest cutoff, that means you know that anything below that will not be propagated, right? So you would see that out of this, maybe this one will be below the cutoff. So then this might not propagate. Okay, if it is below the cutoff, it will not propagate. If the frequency is above the cutoff, then it will propagate. So in this kind of questions, you have to find the lowest cutoff frequency. Okay. Okay. Now, degenerate mode in rectangular waveguides. What do you mean by degenerate? So you can see that you have these different modes which are defined by M and N, right? But there could be many modes which can correspond to the same cutoff frequency, right? So then those modes would be degenerate. Now the question says that out of all these options, which of them are degenerate modes, right? Now, if we just look at the expression for the cutoff frequency, we would know the answer. See, whether we talk about TE mode or TM mode, in all the cases, the expression for the cutoff frequency is the same, right? So that means if your M and N is the same, the cutoff frequency for a TM mode and a cutoff frequency for the TE mode for the same N and N value will always be degenerate because the formula is the same, right? The cutoff frequency is the same, right? Only the difference comes at the starting frequency, the lowest cutoff frequency, right? So in a rectangular waveguide, TEMN and TMMN modes are always degenerate. The above cutoff frequency is the same. Okay. The only condition is that in the TE mode, you can put M or N or any one of them, you can put it to be zero. While in TM mode, you cannot put M and N to be zero. So the answer in this case would be this, right? So all TEMN and TMMN modes are degenerate, but with the condition that M is not equal to zero and N is not equal to zero. Okay. So the answer should be yes. Okay. So now this is another concept of So till now you have been discussing about waveguides. So this is another concept or another important thing about transmission lines that we are trying to discuss now, which is about pulse on transmission line. So now if you have, we know what is a transmission line. Okay, so you would have a source, you would have a load. Okay, but now at the source, if you are transmitting a signal, which is a pulsed signal, right? Some pulse of some width and some amplitude, right? Now, as it gets propagated, we want to see what kind of distortions can come in, what could be the various issues. So in general, we don't want it to attenuate, right? So, but under what conditions the attenuations can come in. So this is what we are trying to understand now. So in consider a transmission line where you have some load. Here it's considered to be resistive just for simplicity uh, case. So here RL is the load, RS is at the source end. Okay. And as you can see, there's the reflection coefficients are non-zero. So they in general might not match, right? So there can be multiple reflections. So the signal can get distorted, and we want to see what happens in those cases. So we have considered the reflection coefficients to be non-zero. Okay. And now you have a pulse that is being transmitted. Now, when we talk about pulse, that means you have something like this, right? Some non-zero value for some time, and then it goes to zero. That's a pulse. Now this pulse can actually be decomposed into this two kinds of signals, right? One is this up signal. Suppose if you have a plus V naught pulse, so what you can see is that for some time t, so you can write it as this. So you can say that one is a all time up, V naught constant scalar signal, and then what you have is you have this, at some certain time interval t later, you have this signal which is minus V naught. So that means now if you add both of them together, you would see that after time t, because this is minus V naught and this is plus V naught, so from t, what would happen? Your net signal would go to zero, right? So this is how a pulse can be written, right? This is one way of writing, or just another way of, you know, writing how one can write a pulse in terms of these two signals. Okay. Now, what is the question that we're trying to address is that suppose, you have some non-zero reflection coefficient, non-zero at both ends, at the source end and at the load end. You know what is RL, you know what is RS, or if you know these values, you can try to find them. But given this condition, what happens to the signal? Okay, so that we'll try to understand that using an example. So suppose we know that the reflection at the load end, reflection coefficient is 1/3. The reflection coefficient at the source end of the generator end is given as minus 1/3. You have a pulse of width 0.1 nanosecond. The voltage is given as 12 volt. The length of your transmission wire is given as 0.09 meter. This is the speed of the light, basically the speed of your wave. Okay. And you say that the delay is given as 0.3 nanosecond. Delay means it's the time for the signal to reach, from the generator end to the load end. This is the time it is taking. Okay. And it's important to know that the pulse width here is less than the time it is taking to propagate. And we would see why this is not good for transmission. Okay. So now here, what you can consider is if you use the values of, you know, the reflection coefficient at the load end, and you also know the load, right? You know the load is 100. So like here, suppose if you know the load, so that means gamma L, you know the load. So you can use it to find the characteristic impedance of your transmission line, right? And if you do that, you would get a value of this. So this is your characteristic impedance of your transmission line. Now that you know the characteristic impedance of the transmission line and you know the reflection at the generator end, so you can use it to find what is the resistance at the generator end, right? So now if you know all these two values, so once you have done these calculations based on the reflection coefficients that you have, this is the circuit that you have at the source end. So you have a 12-volt supply and you have these two resistances. So as we had also done in the previous mini questions, the voltage will get divided, right? So now you would divide the voltage into based on this resistances that you have. So you can say what is the voltage at this end? It would be given as 50 by 75 into 12, right? That is 8 volt. Now this is the voltage at the generator end. Because the impedances are not matched, that means there'll also be a reflection. So once the this is the signal at this end. Now this once it transmits and reaches the load, there'll be a reflection, right? And how much would be the reflection? So that would be given as gamma L into V1 plus, right? So this will be the reflection that will come from the load end, right? So now if we try to plot it graphically, we can do this kind of a plot. So here, as you can see, this corresponds to the source end, Z equal to 0. This corresponds to the load end, Z equal to L. Okay. And here, as you can see, you would have this axis is considered the time axis. Okay. So here at the start, so when you are starting, so you know that you have a 8 volt at the source end, right? Now this 8 volt will take some time to reach the load. And how much time will it take? It will take 0.3 nanosecond, right? So this is how it will reach the load end. Okay. So at 0.3 second, it reaches the load end. Once it reaches there, there'll be a reflection from there. How much will be the reflection? So the reflection will be given as gamma L into V1 plus, which is 8 by 3 volt. That is equal to 2.66 volt. So now at the load end, there'll be a reflection. And this reflection will again transmit back to the source end, taking a 0.3 nanosecond time, right? So again, you can see at 0.6 seconds here, this reflection will reach. And what would be the value of the voltage? 2.66 volt, right? So this is for the case, this is for the signal that started at t equal to 0. But this is a pulse with a finite width, right? And the width is given as 0.1 nanosecond. So what you can say is that as we just discussed, so you can write the pulse as a signal which starts at t equal to 0 with V naught and then at the pulse width. Okay, so now t is equal to the pulse width. At that point, you have a minus V naught coming in so that the net voltage goes to 0. So you can say that at 0.1 nanosecond here, a minus 8 volt starts, right? Then what you have effectively is a pulse. So so here when the minus 8 volt starts, this will again take another 0.3 second. So it reaches here at 0.4 seconds, right? And this is minus 8. Okay. Now once it reaches here, we know the reflection coefficient at the load end. That is 1/3, right? So that means again this minus 8 out of minus 8, minus 2.66 will again get reflected back. Okay. So at 0.7 second, that will reach your source. Again, there'll be another reflection from the source, right? Because this is also not matching. Remember that at the source, the reflection coefficient is minus 1/3. So here, when 2.66 comes here, what would be the signal that would be reflected? That would be minus of 2.66 into 1 by 3. That is minus 8 by 3, right? Similarly, here minus 2.66 comes in. So what gets reflected is 8 by 9, right? And similarly, this signal will again then at after 0.3 seconds will reach the load end. So that's how this thing will continue. So now if we try to see what is the net value. So here you can see that this is at the source end. Okay. At 0.3 second, it would reach the load side. Now from 0.3 to 0.4, what is the signal that you are seeing? So you are seeing a 8 volt here and this 2.66 volt here, right? So basically now it's a pulse of 10.66 volt. Okay. But at this end, so once it gets reflected again and then comes back here, you would see that the effective value now becomes negative. So what is happening is that your signal is getting attenuated. So it's not remaining same. And why this is happening is mainly because your delay time, or the time for it to travel from the source to the load is longer than the pulse width. If this was fast enough, then you would have got the similar signals. So this kind of case where the pulse width is smaller than the time for it is taking to transmit is not a good condition for proper transmission. Okay. Now, based on this kind of, we can do similar kinds of questions. So, in some questions from the last year's assignment was like this, which is quite similar to what we have just discussed so far, right? So here it's a 1 meter long transmission line, and the voltage at the, so it's a pulse of 20 volt with the pulse width given as 0 to 0.5. So 0.5 nanosecond is your pulse width. And you know that this is your reflection coefficient at the load end. This is the reflection coefficient at the generator or the source end. Okay. And this is the load. Load is 100 ohm. And this is the speed of your signal. Okay. And you have to find what is the load. First question says you have to find what is the load voltage at t equal to 3.5 nanosecond. Right. So basically, first, what you have to see is what are the values that are provided here and what we have to find out from here. Right. So here you can understand you have a 1 meter long transmission line. Your speed of your transmission is given as 3 into 10 to the power 8. So from here, you can try to find the time that the signal takes to, go from the source to the load, right? And that would be your TD value. So if I compare with that, with this question, that would be your TD value, right? You again know gamma L and gamma G, okay? And you know RL. So because you know all of this, you can try to find the characteristic impedance of your transmission line and the impedance at the generator end. Okay. So if you do that, this would be something like this, right? So this is what you have. So here, ZL, okay, Z naught has to be found, and you know what is the gamma L. So if you use this relation, you can try to find what is your Z naught. So this is your characteristic impedance of your transmission line. Now, similarly, at the source end, again, you can use this reflection coefficient at the source, right? And from here, you would see that you can you can try to find the resistance at the generator side, which is 25 for this question. So effectively, now what you have is this source here, 20 volt pulse that is coming, and then it would first pass through this 25 ohm resistor at the generator end, and then this is the characteristic impedance of your transmission line. So now you know what you have to do, right? So if you have to try to find what is the voltage at this end, we know that we have to use the concept of voltage divider circuits, right? So basically it would be 50 by 50 plus 25 into 20. So that would be the voltage drop at this end, right? Now, once you have the voltage drop at this end, what you have to do, you know that once it reaches the load end, there'll be a reflection. So you have to find out how much of the wave gets reflected, and that will be dominated by this value, the reflection coefficient, right? So this is what I mean. So you can find V1 plus, which is given as 13.33 volt, okay? But a part of this will also be reflected back, which is 4.44 volt. That is 1 by 3 into 13.33, right? And this is the time that signal takes to go from the source to the load. That is given as 1 meter divided by 3 into 10 to the power 8, which is 3.3 nanosecond. Now, given these values, now you are asked what is the load voltage at t equal to 3.5 nanosecond. So here you can try to draw this diagram, right? So this is the source end, this is the load end. You have the pulse width given as 0.5. So at the starting, okay, you have this 13.33 volt going towards the load. It reaches the load at 3.3 nanosecond, right? Similarly, at 0.5 nanosecond time interval, you can consider a minus 13.33 volt from the source end. And this will reach the load at 3.8 nanosecond. Now, out of this, we know that 4.44 volt will get reflected, right? So this again gets reflected back, as you can see. So now if you're asked what is the voltage, load voltage at t equal to 3.5 nanosecond, that is somewhere here, what would be that value? So you know that you have 13.33 and you have 4.44, right? So if you add the two, that would be your net pulse value at 3.5, right? So from this diagram, this is how you can try to answer this kind of a question. Okay. Now the next part of the question says find the voltage reflected from the load at 3.8 nanoseconds. So this comes right away. What is the voltage that is reflected? That is minus 13.33 into 1 by 3, which is minus 4.44. So this is your voltage that is being reflected at 3.8 nanosecond. Now again, this part of this voltage will again reach the source end, and there'll again be a reflection from the source side, right? Now the question says find the voltage at load at equal to 10 nanoseconds. So that means you have to you have to follow up with this reflection till you reach 10 nanosecond time, right? So you have one reflection, you then again have another reflection at the load end. Here it's important that when you have this reflection at the source end, here you have to take into account the fact that your reflection coefficient at the source is minus 1 by 3. So when you have this signal coming in 4.44 volt at this point of time, when it gets reflected, it will be minus 4.44 by 3. Okay, so that is minus 1.48. Similarly, this signal, which is minus 4.44 here, when it gets reflected, will be plus 1.48. Okay. Now, at the load end, once it reaches there, you know that the reflection coefficient is 1 by 3. So what gets reflected is 1/3 of what reaches here. Right? So now if it says what is the voltage at the load at t equal to 10 nanosecond, that is the sum of the signal, these two signals, right? So it is 1.48. And so you can see it starts from here. So it has already got reflected at this end. So here what you have to do is basically minus 0.49 minus 1.48. So that's the effective uh, voltage that you have at 10 nanoseconds. So that's how you can try to answer this kind of questions. Okay. So yeah, that was about the class. Do you have any question? Okay. So basically what we discussed today was mostly waveguides, which are pretty standard things. Okay. So the main part of waveguides is just this, that there is a cutoff frequency and it depends on risk factors. Okay. So we discussed that and how we derived the TM and the TE modes. Okay. And finally, we spoke about pulse in a transmission line. So that's was about today's class. If there's no other doubts, let's call it a day. Do you have any question? If you have any question, you can ask. Okay. If not, let's call it a day. Thank you.